Hello and welcome. My name is Steve Wilson. Today, we're going to be focusing on some of the more technical aspects of kidney transplantation and specifically what research is currently being conducted that may lead to increased graft health and longevity. Our guest today is Dr. Anat Tambur. Dr. Tambur is the head of the Tambur Laboratory at Northwestern University, and she and her team are currently engaged in research into the immunogenicity of HLADQ antigens and its role in antibody-mediated rejection in solid organ transplantation. Doctor, we are very grateful for this opportunity to speak with you today, and we thank you in advance for your time. How are things on Lake Michigan today?
First of all, thank you for the invitation. It's a gorgeous day in Chicago, wonderful weather, very unique, and Lake Michigan is fantastic.
Awesome, great. So doctor, before we even begin with general questions, could you provide a brief overview of the term immunogenicity, if you would?
Absolutely. When we think about immunogenicity, we need to think about two separate concepts. Immuno, so the immune system, and genicity has to do really with the ability to perform, to develop, or to I'm blocking at a word here, to develop an immune response, right? So like genesis, right? So it's initiation of an immune response in simple terms.
Okay, thank you. And to begin with our general questions, as any living kidney donor knows, the minimal criteria for pairing donor and recipient is blood compatibility. And that part seems easy enough to understand. The second criteria is a bit more complicated and probably less understood by the average layperson, and that is the concept of HLA antigen matching between donor and recipient. So would you give us a general overview of the human leukocyte antigen system, or HLA system, what it does, why we have it, how we acquired it, and then perhaps speak a little bit about its relevance in determining compatibility between donor and recipient in kidney transplantation?
Absolutely. So that really goes into immunogenicity. The HLA system is really one of the key components that controls our immune response. It's called HLA human leukocyte antigens because the leukocytes, or the white blood cells, are the ones that are the most involved in immune responses. Although the markers of the system, which I'll explain in a minute, are expressed pretty much on all cells in our body. And that's really important in the context of transplantation because we're looking not just at the white blood cells, we're also obviously looking at the cells that are expressed on the organs that are being transplanted. So one thing to remember when we're talking about an HLA system, we're talking about immunogenetic, which is a little bit different than immunogenicity. We're talking about the genetic of the immune system. And the HLA system is indeed a genetic system, meaning it's been inherited to the child, half from the mother and half from the father. So every individual have components from each parent, like any other genetic system. But it's important to appreciate that it's being inherited. So you're born with the system, and this is what you eventually have on your cells for the rest of your life. We're talking about the HLA antigens, which are the products of the genes that are being inherited. And those are cell surface molecules, receptor in a sense, if you want to think about it like that, that are part of two major families. People are talking about HLA class 1 and HLA class 2 that are a little bit different molecules, and they have a little bit of a different role, but they are both part of what we talked about, the immune system. And the critical thing to understand about the HLA system is that its role is really to maintain health. The transplantation part is on the side. It's actually come to as an obstacle, if you think, when we're talking about transplantation, but really the system was developed in order to protect the body. What we need in our body is to have a system that will signal the immune cells that we have an invader in the cell, whether it's a virus or a bacteria or a fungus. We need to have a way to tell the immune system, listen, this is something that does not belong here. Let's get rid of this. And what the HLA antigens on the cell surface do is there's an amazing process that we're not going to go into that allows the cell to internalize the invaders. So viruses will go on their own. We can engulf bacteria and things like this, process them in the cells, generate small peptides, and those peptides are actually presented in the context of the HLA molecule. So if you want to think about it, an HLA molecule would look something like this, like a receptor, and the peptide will be presented in the context of it. And now you have something on the cell surface that the surveillance of the immune system, the other cells that look at the what's going on in the body, that constantly check what is happening, can see as if like something is wrong here. So that's really the principal role of the HLA system, and that is why it is so important. The other thing that you were asking about is how does that important to determine compatibility between donor and recipient. So let's think about the fact that I have half of my genes from my father, half of my genes from my mother. I have those HLA molecules on the cell surface. In completeness, we're actually looking at 6 different genetic loci, so 12 different HLA types of HLA antigens, HLA A, B, and C that are part of the class 1, HLA DR, DQ, and DP that are part of the class 2. And this is what defines me immunogenetically as Anat, right? This is my picture. The HLA system is extremely polymorphic. So other than the fact that we have all those different loci, per locus, we have many, many variants that different individuals can express. We call them alleles. And those actually, when you do, people talk about HLA typing, when you actually perform molecular testing to look for the DNA sequences of those molecules, those per individual are more unique than fingerprinting. So if we look at you and me, the likelihood that we have something that is, on one of those loci that is shared, it's relatively low. It becomes even lower when you're talking about different ethnicities, different races, and it's really very specific to an individual. When we are transplanting an organ, we're transplanting the cells with the organ, and those are covered with the HLA antigens of the donor. So now my immune system as the recipient will see different HLA antigens that will be viewed by my immune system as foreign, and that's why I will attack those cells. And this is why we have rejection. So this is really the key importance of the HLA system in transplantation. It's a wonderful system to maintain health. It's an impediment when we're talking about transplantation.
So growing up as a child, my mother told me the only thing I needed to do was stay healthy, was eat my vegetables. You're saying that's not actually accurate.
Well, you still have to eat your vegetables,
okay,
but it's really important. You're eating your vegetables will keep your immune system healthy, so it can fight all those invaders.
Got it. Okay. So as a kidney donor, I often hear the terms perfect match or 6 match or even 6 mismatch when referring to donor-recipient compatibility. What does it mean to be a perfect match versus a 6 mismatch? And is there a discernible difference in graft longevity within that spectrum?
Absolutely. So I actually talked, and I wanted to make sure that people understand that the HLA system have those 6 loci, 12 different antigens. So why are we talking about a 6 match? And that's really, really important. The history of the HLA science is relatively recent. Well, it's 60, 70 years old. But we've been growing in leaps and bounds. Tremendous progress, definitely in the last 25, 30 years. When the HLA system was recognized, at the very beginning, we thought that there was only one locus, then we realized that there are two, and then three, and later on came the others. Those HLA antigens that were recognized first are HLA-A, B for class 1, and then DR from class 2. And for many, many years, there was some stagnation in what we understood. We started realizing that there are more alleles within each of those loci, but we kind of remained within this understanding. Really, we needed a significant leap in technology to move into molecular testing and so on and so forth to recognize the other loci. The rules, the set of rules that UNOS came about with and other entities around the world looking at transplantation were formulated around the time that we understood about HLA-A-B-DR. And the understanding was that HLA matching is important. So let's try to match for A-B-DR, 2 antigen per locus times 3. Here is your 6th match. So matching for A, B, and DR. You ask if there is a correlation to transplant outcome. And there are numerous studies that show that HLA matching will definitely give you a longer longevity of the graft. Why are we not trying to constantly match for HLA? That really has to do with issues of equity. The major rules for transplantation come for the deceased donor transplant, not so much for living donor. Living donor, you can choose your recipient or you can choose to donate to different entities that help facilitate organ transplantation or kidney transplantation. But the vast majority of the transplants are coming from deceased donors. There is a mandate, a federal mandate that looks into equity in transplantation. And then it's equity in access that has nothing to do with HLA. It's equity in receiving medications and support, so on and so forth. The one part that it has to do with HLA is that matching part. As it stands, and there are multiple reasons associated with this, the majority of the deceased donor organs are Caucasians. I've mentioned earlier that the HLA makeup as ethnicity can change over ethnicities, right? So if you have more Caucasian donors, and unfortunately you have significantly more African American patients that need transplant because they have more problems with blood pressure, because they are more prone to kidney disease. There are some genes that are involved in kidney disease and so on and so forth. There is that imbalance, and because HLA travels with ethnicity, that creates imbalance in matching. If you mandate matching, that meant at the time that African Americans waited on the transplant waitlist much longer. So the role of matching was eliminated in order to improve equity.
Okay. And continuing with the theme of matching, so a third criteria to donor-recipient compatibility is a concept called cross-matching, and the requirement that a cross-match for donor HLA antibodies be negative. So can you explain what it means to have a negative cross-match versus a positive cross-match, and what factors might cause either to occur?
Absolutely, and that's really a beautiful continuation from the previous question. When people, well, early on in the days of transplantation, and I want to mention the person who really contributes to this understanding, it was the late Dr. Paul Terasaki, who made tremendous impact on our field. But what he had shown in a seminal paper New England Journal of Medicine, 1964, is that if you take serum from the patient and incubate it with cells from the donors, and the most accessible cells are lymphocytes because it's just a blood draw, it's easy to get them. Also, lymphocytes express both, at least the B cells, both the class 1 and the class 2 antigens, so they're a really good source to look at it. You can look at the donor serum and see if it has antibodies that can recognize donor antigen, and you can do this in vitro before you go into transplantation. This is what we call the cross match. And if you do this prospective cross match and you find out that there are antibodies that recognize the cells, meaning that the cross match is positive, then you know that the likelihood that that kidney to be rejected is extremely high. And there's also a correlation with how much antibodies. If you have a lot of antibodies, you can have what we call hyperacute rejection, so the kidney can turn black on the table. And if you have no antibodies, the cross-match will be negative. And then, at least at the peri-transplant time point, the patient will be good to go. The kidney is going to be accepted. There are a lot of other factors, obviously, that will come on later on that can help protect that. But that's the cross-matching. We are now moving into something that is called virtual cross-matching, which I would assume a lot of potential living donors will hear about. What we can do is, now that we have the tools, we talked about the advances in molecular typing, we can actually type the donor HLA antigens, all of them, the whole 6 loci, the whole 12 antigens. And once we have those, that information, we can perform on the side tests to identify the specificity of the antibodies. And like a little, I don't know, there are those kids games when you're little that you are connected between 2 different dots because they have something that shares together. So if I have antibodies to A1 and the donor has that N1, I know it's going to be positive. So we can actually do this virtually. We don't necessarily have to do a physical cross-match. We don't have to put all the things together. Usually people still go ahead and do the physical cross-match, but the first step in thinking about matching, and definitely we have the time for this when we're talking about potential living donations, is you do this virtually. And if it comes to be extremely positive, then there's no point in continuing forward, other than some cases that we may mention a little bit later, but in principle.
Okay. And with HLA antibodies, what does it mean when somebody is overly sensitized or highly sensitized? Can you explain like how that happens? What causes that to become a condition, and does it affect them as it relates to the overall donor community?
Right, and this is a really, really important question. Again, our body looks at something foreign and develop antibodies to it, or have a cellular response to it. Why would we develop antibodies to HLA? And that's a really intriguing question, right? I mean, where do you get exposed to foreign HLA to actually generate antibodies? So we're not born with those antibodies. It's an active process. So one thing that I find extremely fascinating, and it's a huge field of interest, is the whole issue of pregnancies. When you think about pregnancies, this is actually a normal physiologic situation that many women get to enjoy, where they're growing internally something that is half of their genetic system, but also half of the paternal partner HLA system, or a lot of other genes. What happens in the womb, and this is really interesting from the concept of learning about tolerance. In the womb, there are mechanisms that will protect the fetus that is half identical to the mother, but half different, right? Hemi-transplantation, if you want to think about it in these terms. There are mechanisms that help protect it. Unfortunately, there are some women that those mechanisms don't work well, and that leads to multiple spontaneous abortions, for example. So people are trying to understand that. But once the fetus is born, then you have a different connections between the now newborn and the maternal blood system. So you have the exposure to the paternal antigens, and these things actually sensitize the mother against the paternal antigens on the fetus. So one of the major sources that you will find people developing antibodies, women, are multiple pregnancies. It doesn't mean that it always happens, and this is again a very important area of research. Why is it happening? Can we understand what is driving the immune response? I want to kind of pause here, and I'll keep on talking about other things that cause sensitization. The importance of matching, as we said before, is tremendous. But we know that getting to this for all patients is going to be impossible. So one of the things that we can learn from pregnancies, and then from a lot of other areas of research, is to look for what we consider acceptable mismatches. Why sometimes an individual is exposed to certain HLA antigens and they don't develop antibodies, and are those other antigens sufficiently similar, not identical, sufficiently similar to somehow, I don't know, trick the immune system to think that they're not so bad, or at least, yeah, not that they're okay, but they're not so bad. So I'd be happy to talk about this a little bit more, if you will. But other sources for sensitization, patients that get transfusions, even platelets carry HLA antigens on them, right? Definitely if you actually get cells, you're getting someone else's immune system and you develop antibodies. And of course, transplantation. And unfortunately, a lot of patients will need a second transplant and a third transplant. And for the vast majority of them, we see that as they reject an organ, they develop antibodies. Actually, the worst rejection of an organ is what we call antibody-mediated rejection. There's a cellular mediated. We have good drugs to control those. Antibody-mediated rejection, right now, we don't have a lot of good drugs to control it. Eventually, it would lead to graft loss. And then that patient will need a second transplant, but now they have a lot of antibodies that they develop as a result of that transplant. So pregnancies, transfusions, and transplantation.
Okay. And you mentioned, please, go
sorry,
ahead.
You wanted to talk about, I'm fine to have another question, but you wanted to ask about how it's being calculated, the highly sensitized, right? Mm-hmm. So, and I think that is an important concept. So we look at antibodies against a panel of antigens. So here comes the term panel reactive antibodies, or PRA. And UNOS came up with a system that allows you to calculate, given this universe of antibodies, how many of the potential donors are going to be blocked from being a compatible donor with you. So we talked about matching. Compatibility means that currently we don't have antibodies to a particular individual. What UNOS had done, and that happened about 10 years ago or so, they looked at the universe of donors, effective donors that they actually had used, looked at their HLA antigens, and calculated, it's a pretty complicated calculation, what is the frequency of the different antigens in the donor population. It's complicated not because it's not enough to look at how many times donors have, or how many donors have A1, but the HLA system comes with what we call linkage disequilibrium. So if I have A1, I'm way more likely to also have B8 rather than B64, for example. So you need to actually have this computational system to say how many times you're likely to have a donor that have this, and these antigens together. And obviously it's a percent of the population. So people are talking about percent CPRA. The higher your percent CPRA, the less likely you are to find a compatible donor. And on a side, again, this is more for the deceased donor or patients awaiting deceased donor transplantation. Once you reach 98%, you're considered extremely highly sensitized. And for those on the wait list, they start getting significantly higher jumps of points that would advance them in the system. So if you have 100% CPRA, your likelihood of finding a compatible donor is a needle in the haystack. How can we help you? Going back to equity, we can put you higher on the wait list, or for those donors, they actually get a deep in all the donors in the country, not just in their local area or region, right? So, yeah.
Okay. And despite all the advances then, doctor, that have been made in compatibility and all, we know that transplantations are sometimes subject to chronic rejection over time just due to immunogenetic response, or in layman's terms, mismatch of underlying epitopes and eplets between donor and recipient. So I believe this is also a cause for de novo donor-specific antibodies, or de novo DSA as they're called. Much of your specific research focuses in this area. So can you first explain, what are de novo specific antibodies? And second, can you discuss how your research in the area of immunogenicity, epitopes, and eplets is taking organ grafting to a new level of understanding and success?
All right, so we kind of weaved our way towards this, talking about compatibility, talking about the fact that we need to, one, cross the barrier of not having antibodies at the time of transplantation, but then with time, the organ, as long as it's, other than the fact that it's a full match, will still work on the immune system to cause what we call chronic rejection. Chronic rejection is often caused by antibodies or antibody-mediated rejection. And as we said before, this is also something that we don't have a lot of good tools in the immunosuppression armamentarium to treat. What we realized in the last 7-8 years, maybe a little more than this, is that there is one group of antibodies that is the main culprit in causing chronic graft rejection or eventually graft loss. And those had to do with HLADQ. Now, we talked earlier on ABDR, right? It's not, HLADQ is not part of the glorious 6, right? It's not part of the matching algorithm. We developed tools to look at HLADQ better only about 15 to 20 years ago. And it took time until we were able to look at what is the correlation between this and transplant outcome. And I think today it's proven beyond doubt that the worst mismatch that one can have is HLA-DQ, because if you have a mismatch for HLA-DQ, you're more likely to develop antibodies. Again, not always, and this is really where we need to understand things. I want to pause for a minute and explain something about how we're naming HLA antigens, because that would lead us into eplets and epitopes and so on and so forth. Remember, when the system was recognized, we thought that we have only one locus, and then we realized that there are two, and so on and so forth. And there was no particular reason to give an antigen that was found a name. So they just literally called them 1, 2, 3, 4, and kept on running with the names. Then we realized that actually 1 and 2 and 3 are part of one family of one locus, and then 4 belongs to something else. Nomenclature became a mess. And until now, nomenclature in HLA is extremely arbitrary. We're giving an antigen or an allele a number because this is kind of hierarchically where it was determined or where it was identified in the sequence of time. Nothing to do with their functionality. We did realize, even before I came to the field, that there are antigens that are more similar to each other than others. So we started thinking about them in what we call cross-reactive groups, or CREGs. And even before we're able to do the sequence analysis of the DNA or the proteins, but just by looking at antibody responses, we realized that there are antibodies that will recognize a group of antigen, for example, but not others. So that started people think about there must be something that is shared between some HLA antigens that is different from the others. And people started to use the concept epitope. Epitope is a very common concept in immunology at large. An antibody recognizes an antigen. It doesn't recognize the big molecule, right? Someone recognizes me, for example, they can recognize me by my glasses. They see me as the whole antigen, but that would be the epitope, the thing that would, their eyes would zoom in and say, okay, right, that's the recognition. This is what antibodies do. They recognize epitopes on antigens, and the epitopes are therefore a smaller portion of an antigen, and antigens usually will have more than one epitope. They can have, I don't know, 5, 10, probably not more than this. It will probably stay in the single digit, but still multiple epitopes per antigen. And then some HLA alleles or antigens can have the same epitope, so an antibody can recognize this antigen and that antigen just as well, and some will have things that are very, very unique to them. And we're starting to think about this. We're starting to think about a system that would make sense immunologically to give names, right? I don't care about the fact that someone called this antigen 154. It doesn't give me any sense of what it is, right? And there isn't something that is called 154, but it doesn't matter. But as an antibody, right, as someone who studies antibodies, I want to look at HLA antigens from the perspective of an antibody. How would I look at those HLA molecules? And the last decade, there are a few groups that are trying to look at HLA epitopes. Now, we talk about it, the concept is maybe not simple, but not extremely complicated to try to identify those epitopes. It's getting to be extremely complicated. What we can do is we can type the DNA, it's a strand of nucleic acids. We can type the protein, or if we have the DNA sequence, we can convert it into a protein. So we have a stretch of amino acids, but the antigen itself is a very elaborate molecule, very convoluted on itself. And what we're missing is this 3-dimensionality component. So what people have done, and there are actually several software in the field that look at what we call applets. Applets are those short segments of either amino acids or DNA that we can compare the recipient HLA DNA sequences to the donor HLA DNA sequences and talk about, okay, here are all the differences that we see, and we can count the number of applets, and there's a body of evidence. A lot of it is coming from the group of Peter Nickerson, a transplant nephrologist in Canada, that show that the higher the applet mismatch load, the more likely those patients are to have rejection episodes, developing antibody-mediated rejection, and so on and so forth. All of those studies, which I think are phenomenal, but all of them are retrospective. So you can look at the group of patients that develop those antibodies and retrospectively explain why that might have happened. It's important to appreciate that this is still not at the predictive stage. You cannot project that ahead of time. People are trying to look into this. I'm very much against this. And this is because I have seen, and a lot of my colleagues had seen, pairs of donor recipients that the recipient develop antibodies, and they have very, very few applet mismatches. And what I'm trying to promote, and again, it's not just myself, there are other investigators that are looking at this, that say not every applet was created equal, or not every applet has the same value, right? There can be applets that will be significantly more immunogenic, going back to our immunogenicity. They are more likely to elicit an immune response, and there are those that are less. And it's not just elicit an immune response, but it's elicit an immune response in the eyes of the recipient. So it's always, when I was little, my mom told me you need 2 to tango, right? And you need to look, you can have an amazing dancer, but the partner is going to be me who doesn't know how to dance. It's not going to come out really well, right? So we always need to look at the things in both ways, and this is really where a lot of my research lies. So one, I focus on HLADQ because we know that these are the most common donor-specific antibodies that people would have post-transplantation. Those are the most detrimental de novo DSAs that are coming. So they're more associated with graft rejection, they're more associated with graft loss, they're more associated with inability to respond to any treatment that is coming to them. And then what we're trying to do here is try to figure out, one, which of those mismatches at the molecular level is more immunogenic, and two, where I think is going to be even more important, which of them can be considered acceptable mismatches, right? So we will get to a point where we're not going to find a complete match. Finding a complete match is an extremely difficult task. We know this from the stem cell side of things. Patients who need bone marrow transplantation because of hematological cancers, some of them will have a relative who's a match, usually a sibling, but some of them have more unique HLAs, and they need to look at huge repositories of potential donors. For example, the NMDP, the National Marrow Donor Program, have a repository of millions of people, and even there, not always everyone can find a match. So understanding what is acceptable mismatch, it's not going to mean that we're not going to have any immune response to it, but hopefully we'll have those that with relatively low levels of immunosuppression, we can keep those responses on check. It's not something that would cause significant or severe burst of immune response, not extremely immunogenic.
Okay. And doctor, in that answer, you made reference to stem cell. And I know that Northwestern is pioneering some research on simultaneous stem cell kidney transplantation. And I think some people believe this could revolutionize the transplant industry. So could you give us your comments on that stem cell kidney simultaneous transplant, and what the future might hold there?
Right. So I mentioned a word before, tolerance. And the whole concept of tolerance is to try to get people into transplantation, accepting this organ, while specifically this organ, so kind of making the immune system oblivious of the transplant while still maintaining intact immune responses to everything else. One of the bigger problems with receiving immunosuppression is that the whole immune system is being kind of diminuted, right? So you have less responses to viruses, you have less responses to the organ, you're more susceptible to become sick as a result of this. Not talking about any of the other multiple side effects that you get from immunosuppression. Induction of tolerance, hopefully, will allow people to accept an organ without having to go through this many years of immunosuppression. So there are several groups who are working on this. The one at Northwestern, I believe, is the most unique of them all, but of course I'm biased. And it's spearheaded by Joe Leventhal, who is our chief of the transplant program, interim chief of our transplant program at this point. And what Joe is doing together with Suzanne Ilsted, who is the person who actually initiated that particular path of transplantation. What they're looking for is transplantation of stem cell, and that on its own is a little bit risky because if stem cell from mismatched HLA donors. So we talked about, trying to find that needle in the haystack for those hematologic cancer patients. What they're doing here is knowingly taking a donor that is HLA mismatched. Suzanne Ilsted's contribution, ingenious contribution to this, is identifying a cell population that is called facilitating cells that help in facilitating the acceptance of a mismatched bone marrow or stem cell transplant. The risk in doing this are extreme. And it needs to be very, very clear. If you transplant stem cell, you're actually transplanting an immune system, right? So we're talking about kidney recipients that can reject the organ. If you're transplanting the immune system, that immune system, that foreign immune system, can see the body as foreign and try to reject the body, right? So this is called graft versus host disease, a horrible, horrible disease. So for the study that Joe is doing, Dr. Leventhal, this is really the main concern that everyone had around this. And I'm happy to say that of a cohort of close to 40 patients that he already transplanted only, and I'll have big air quotations, only 2 patients had GVHD. One of them passed away as a result of this. But so it's like only 5%, which is, we didn't think that that can be achieved, but still, it's not a small number. So that said, though, what happens is once you transplant first the immune system and it's being accepted, and that did not happen in all the patients as well, but more than 80% of the patients did accept the stem cell transplant. Now you're transplanting the kidney from the same donor. So you have the donor immune system and the donor kidney, you're not rejecting the kidney. So those patients that are successful in this particular study are able to be weaned off immunosuppression completely. I think it's very risky. I don't want to diminish at all the risks that are associated with this. No guarantee in success. Even if you don't have GVHD, there are some patients that did not accept the stem cell transplant. But those that did received a kidney transplant and are off immunosuppression, which is totally unbelievable. So what Dr. Leventhal and Susan Ilsted are doing, and I have a little project to work with them, trying to look at, okay, what are the differences in immunogenicity of those successful transplants versus those that were not successful. Hopefully, within the next few years, it can be tweaked into something that would yield a higher success rate. It's pretty high as it is, but not as high and as I think we should go for. So anyway, anyone who's interested in this, Dr. Joel Leventhal, Northwestern University, he can provide way more information about this.
You have provided ample information. Dr. Tambur, you've been very gracious with your time and even more generous with your knowledge. We appreciate it so much. We look forward to speaking with you again. Good luck with your continued research.
Thank you very much. And if it's appropriate, you can provide my email information with the videos. If people have more questions, I'll be more than happy to try and answer those.
I will pass that on to Ned. We thank you for your time. This has been fantastic.
All right. Thank you very much.
Have a great day. Have a great weekend. Thank you.